Everyone, today let's look at QP112 asking us what is the maximum number of intersection points of diagonals inside a convex n-gon? When you look at this question for the first time, it's pretty daunting. You're like, what the hell, how do I even calculate this? So the strategy to solve this, obviously when I first see this, I have no idea how to solve it. So one, you start with some examples, and then number two, we work through a bunch of examples until we maybe find some type of pattern, and then from that, maybe we can derive some type of formula. So this is our strategy right here. First of all, what is an n-gon? Well, it's just going to be some shape with some number of sides that's convex. So for instance, a hexagon or a pentagon or, those type of things. Now, the smallest possible convex shape that I can think of is going to be a triangle with 3 sides. So how many intersection points of diagonals are inside a triangle? We're talking about the maximum, keyword maximum, number of intersection points of diagonals inside this triangle. And a diagonal is just something that connects vertices. So we have 3 vertices in a triangle. So the number of ways to connect them, well, they already kind of are connected, right? Just by the fact that they are triangles. So there's 0 ways to connect these diagonals such that they intersect, right? So intersection points here is 0. Now we move on to a bigger shape. Let's say maybe like a square that has 4 different vertices, right? 4 different sides. Now I can actually draw diagonals for this vertex here. The only diagonal that I can draw is to this vertex over here. And then for these vertices, I can connect them with this. Boom, we have an intersection point right there. That's the only intersection point that we're ever going to get. So the maximum here is going to be 1 for a foregon. All right, now let's look at a shape with 5 vertices, for instance, a pentagon, and let's just draw out all the diagonals. So I have 1 here, I have 1 here, I'm going to have 1 here, I'm going to have 1 here, and then I'm going to have 1 here as well. So how many intersection points in this case? Well, we can just count them. I have 1, 2, 3, 4, and 5 that I can see. So it looks like 5 intersection points in the case when we have 5 different vertices. Is that the maximum though? Well, if you play around with this a little bit, you'll see that this is pretty much the maximum that we can do. It's just because the definition of an intersection point is when we're going to have 2 or more kind of diagonals meeting in the same position. So I know it's not the best drawing, but if we have a 5-gon like this, where these are our 5 vertices right here, well, in this case, how many intersection points would we have? We'd only have 4 here, and you can see that it's not the maximum because this point right here has 3 diagonals meeting to create it. So we're going to know we maximize the number of intersection points if all of them are just the sum of 2 diagonals meeting instead of any more, like in this case. All right, so now let's keep trying to find a pattern. We move on to a convex 6-gon right here. I know it's not the best drawing again, but how many diagonals can we have? Well, this one can connect here, here, and here. This one can connect here, here, and up here. This one can connect here as well, and this one can connect up here. Then we have this diagonal right here. So every diagonal is connected 3 times, so it looks good. So what is the number of intersection points, and is it maximized? Well, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and it looks like I have 13 here. So are the number of intersection points maximized? Well, you can see that this one in the middle is a connection of 3 different diagonals. So we can actually increase the number of intersection points just by splitting up this diagonal into multiple intersections, right? If you think about it, I can basically shift over this vertex a little bit, and when I do that, I'm going to get something like so maybe. I didn't draw them very precisely, but you get the idea. And when I do that, I increase the number of intersection points in the center here. Now, instead of having 1 in the center, I'm going to have basically 3 different ones, right? 1, 2, and 3. Now when I count these up, if all of our intersection points are just the connection between 2 diagonals, then I know I have the maximum, and in this case I do, and I'm going to get 15 different circles that I have here. So 15 for a convex 6-gon. So I'm not going to go on drawing past a 6-gon, but you can kind of see a pattern. Maybe you notice that these numbers right here are appearing in Pascal's triangle, right? So just because we just did Pascal's triangle in QP109, you can notice that we're getting elements right here on this diagonal. If you went on to do the example when we have 7 different, you'd find that we would get 35, which again is the sum of these 2, right? So maybe you notice we were getting numbers from Pascal's triangle. I mean, it would have been more obvious if we did out the n equals 7 case and we got a 35, right? But maybe the more obvious pattern is something that we've already been talking about. Is that in order to maximize the number of intersection points, we want every single one of these intersections to just be the sum of 2 different diagonals and nothing more than that. So every single intersection point can be uniquely described by the 2 diagonals that meet to create it. And a diagonal can be uniquely described by the vertices that it runs between, right? So this diagonal right here, uniquely described by these 2 vertices. And the other diagonal that creates this green intersection point can also be uniquely described by these 2 vertices in this case. So when we're maximizing the number of intersections, well, every intersection point is just going to be the combination of 4 different vertices. We have n total vertices in an n-gon, right? So if we have n vertices and 4 of them uniquely make an intersection point, well, then we're going to have n choose 4 different intersection points. So quick recap, in order to maximize the number of intersection points, we want to minimize the number of diagonals that are needed to create them, which in this case is going to be 2. We need at minimum 2 diagonals to create an intersection point, obviously. And for every set of 2 diagonals, they're uniquely described by 4 different vertices. We have n total vertices, so n choose 4 different intersection points. That's why we were getting these numbers in Pascal's triangle, right? This is the row corresponding to 4. This is 4 choose 4. It's going to be 1. This right here is 5 choose 4 right here. This is 6 choose 4. This is 7 choose 4, etc. So maybe you notice the pattern first just by doing a bunch of examples, or maybe you did it this way, and either way you're going to find that it's going to be equal to n choose 4. Doing out a bunch of examples is helpful to find some type of visual pattern that you can think of. In that case, we just did Pascal's triangle, so it came up pretty naturally. So the maximum number of intersections between diagonals in a convex n-gon is going to be n choose 4. We set up a 1-to-1 correspondence between the 4 vertices that uniquely describe the intersection points and the intersection points themselves, and that's how we found this answer.